And does this thing ever converge? It does not, actually. If you look at R12 tilde, which I have erased over there, okay, it's R12 plus R23 e to the I K2Z 2H over R1 minus R21 R23. To study if this integrand or this integral converges, you start to look at the asymptotic values of each of the terms you have inside the integrand. So when k rho becomes very large, what happens to this Fresnel or generalized reflection coefficient? When k rho becomes very large, you want to figure out what happens to this integrand or this integral as you integrate very far out. What happens to that reflection coefficient when k rho becomes very large? Goes to what? Unity.
R1.
Not necessarily. Not necessarily. Okay? But let's look at this term. What happens to K2Z when k rho becomes very large? Becomes exponentially, becomes imaginary, right? And then this will become exponentially small. This will become exponentially small. So when k rho becomes very large, this becomes R12. Okay, R12 is not necessarily equal to unity because if you just take the simple TE case. TE case is this one, right? Mu being the same. What happens to K1Z and K2Z when k rho becomes very large? It becomes just IK rho. IK rho. They cancel each other. Actually, R12 becomes 0. Then, if it is the Tm case, you should have this term in there, and then it becomes epsilon 2 minus epsilon 1 over epsilon 2 plus epsilon 1. It becomes the static reflection coefficient for static fields. If you have studied static, electrostatic before, this is the reflection coefficient for static field. So it becomes a constant, or sometimes it becomes 0. And with 0, it becomes small, but actually it becomes something algebraically small, not exponentially small. That means that if you had in a T case, it would be 0 plus 1 over k rho square or k rho term. Okay. So this is no good because this potentially can just tend to a constant when k rho becomes large. So that's not going to help with the convergence. What about the Bessel function? What does it become when k rho becomes large? How fast does it decay with k rho? Right? Remember that, right? Many of you are very good already. You remember that this is equal to 2 over pi k rho cosine of k rho minus pi over 4, right? So this is only algebraically small, and then other than that, it oscillates. So this is not going to give you good enough decay. What happens to k rho cube? Becomes algebraically large. K1z becomes what? K rho, right? So you have k rho squared here, constant here, 1 over square root of k rho here. This thing is never going to converge. Never going to converge. Okay, so what do you do if it never would converge? What?
Introduce that loss.
Huh?
Introduce that loss.
Some loss. Really, that doesn't help actually. Even if you make K1Z have some loss, you make all the KIZs, all this asymptotic analysis still hold true. Okay, introducing some loss wouldn't help here. So what can you do?
Grab some first terms.
Right?
Grab some first terms.
Grab some first term. Okay, there's one way. Okay, grab some first term. What do you mean by grab some first term? Can you say more explicitly what do you mean by grab some first term? No, not quite. What do you mean by grab some first term?
Just take first several terms and add them together.
What do you mean by take the several first term of this and add them together?
No. First, several inputs.
Several inputs. Okay, there's a quick remedy, but not a good remedy. Yes?
So well, the cancellation occurs if you integrate from negative infinity to positive infinity.
Right?
Instead of one branch only.
Yeah, you can do contour deformation too. But there are many solutions, so that's one possibility. Very good. One quick and dirty way is to not take this term out. Make z plus 2d1 not equal to 0, because this was responsible for exponential convergence. If this term had been there, k1z would become pure imaginary, and this gives you exponential convergence. But that's a quick and dirty way, right? But what happens if your boss insists that you solve the solution right at the interface? Z plus 2d1 is right at the interface, so this term goes to 0. Okay? So you can do a lot of things. You can do a lot of things. One thing might be similar to what you say. Try to collect the first few terms and try to integrate them in closed form. Okay? Say if this tensor constant, can I integrate this in closed form? Because I know that this tensor constant, the leading order term can be integrated in closed form, right? Remember where this comes from? This has a closed form solution. And this comes about, remember, came about because of what? Where did it come about? It came about because of this. K rho square is equal to K1 square minus KZ square. So it comes about because of this. So I can rewrite this as 1 K1 square plus partial square partial Z square d K rho over K1Z J0 K rho. Right? This K rho cube. But this has a closed form. What is it? E to the IKR over R, right? Sommerfeld identity. And then after I obtain that, I evaluate this on that, and then I get a closed form. So I can at least integrate the leading order term in closed form. And then I think about how to integrate the next higher order term in closed form, next higher order term in closed form, until I reach a term that I can evaluate numerically. Okay, so in that case, try to exercise your brain a little bit, and then try to find closed form solutions to terms that cannot be numerically integrated.
Shouldn't there be another exponential term?
No, I'm saying that.
Because only then you can reduce it to k rho cubed, right?
Right.
So only because of exponential of ik rho.
Yeah, I can make z as small as possible. This identity will still be valid, right? And then I can find a closed form solution for this differentiated with respect to z after that. There's still z value in here, and then I can find closed form solutions, and then you can collect the next order term and then find as many closed form solutions. Then you have to go back and exercise your brain to find those closed form solutions. So there's no escape from using your brain. Sometimes you have to use that. Okay.
Excuse me, about the power of the 2B power of K rho extension written as this extension. This is something like extension with green function.
Right. This is the Sommerfeld identity, going from here to here. It's the Sommerfeld identity with z equal to 0. Okay. I can integrate this in closed form. This expression is valid even when z is equal to 0. Right? So you have to do clever tricks like this sometimes in order to find solutions of this. I guess we'll stop here and reconvene again this Thursday at 9 a.m. Okay, it's going to be late to class.